right, this morning we are going to talk about the beginning of discussions about AC, alternating current. And in first semester you studied DC, direct current, where everything adds up nice and neatly. That time is over, gone. AC does not add up directly. It just doesn't do that. Sorry. Okay, so. Okay, we're going to talk about the difference between direct current and AC. We're going to be able to compute instantaneous values of voltage and current for a peak sine wave, because we're going to talk about how AC is made. Be able to compute peak RMS and average values of voltage and current. Discuss phase relationship or voltage and current in a pure resistance circuit. Remember, we talked about pure resistance circuits because it keeps things simple. Okay. Single greatest advantage of alternating current is that AC current can be transformed and DC current cannot be transformed. Now, where did that argument come about to begin with? 1904. 1904? That's a pretty particular year. Why 1904?
World's Fair.
The World's Fair. Who was arguing about how we should create power? Westinghouse and Tesla and Edison and his DC power supply. He thought that DC should be the power supply of the world. But if that's true, since you cannot transform DC, that means you're going to have a generator on every single street corner. And that generator will supply just that one block, because the wires can't get too long, right? Because in DC, the voltage drop becomes horrendous fairly quickly, right? So that being able to transform voltage into power into a higher voltage with lower current and get it someplace without any voltage drop and then bring it down to a useful voltage becomes a very important factor. Okay. So alternating current. This is a really bad sine wave, but current is generated in a sine wave. Okay. Okay, battery. Well, that's not a very good idea of how to do this. Let's not do that. Let's talk about how AC is really made. Now, basically, let's see if I've got a slide that's going to show this anyway. I hate when that happens. Okay, so AC is generated by spinning a winding around in front of a magnetic field, right? Now, it doesn't matter whether it's single phase, three phase, AC is generated this way. This is kind of a bad picture, so I'm going to add a few things to this thing. So let's say we have a magnetic pole up here, and this is the South Pole, and we have another pole down here. It's a North Pole. And we're going to come over here and we're going to say the rest of this thing is over here. And we're going to start out and we're going to call this 0 degrees. Okay? Everybody all right with that? So as this winding or this wire or a bunch of wires, we're going to look at it as just one wire. But really, you know that in an alternator, that it's a bunch of wires going around this magnetic field, right? It's going past the magnetic field. So we're going to look at it down here. It's as far away from the pole of the magnet as it can be. And it's not anywhere near 90 degrees to the magnet. So down here, we know how much voltage is being generated down here. Nothing. Nothing. But now let's look at when we get up here. As the wire goes past this point, it's almost directly perpendicular to the magnetic field, and it's close. And so as it goes past this point, at this point right here, we're going to generate peak. That's the peak of what we're going to generate. So 100% of whatever the peak voltage we're going to create is right there. That's when it's going to happen. And how far across in degrees is that? That's 90 degrees. Everybody agree with that? Okay. Now, back here, this is 180 degrees, right? And how much power are we generating back at 180 degrees? Nothing again, right? It's dropped back down to zero. Now, as this thing keeps going down here towards a different pole, and it's getting closer and closer to this magnetic field, it's generating more and more as it goes. Everybody agree with that? So when we get down here to this center point again, it's going directly across the magnet, and it's going to generate what right down here? Peak voltage again, okay, in a different polarity, okay? This is one magnetic pole, and the magnetic polarity of that voltage has a direction. It's going forward, okay? Now, when we go here, from this point down here, it's the opposite polarity. So it's going to create a different direction. So it's going to turn around and go the other way, literally, okay? But we have trouble showing that. So here's a point where we're going. Now, a couple terms you need to know is peak to peak, top of the wave to the bottom of the wave. You'll hear that in electronics. You'll probably never hear that as electricians. But electrical work is becoming more and more electronic, right? Everything's becoming solid state control, right? Okay, so you need to know more and more electronics as time goes by. So the peak, though, is from the 0 point up to the center point, up to the very peak on one direction. Okay, now we need to talk about what RMS is. Let me come back to that. So we have this wave of the power that's being generated, the voltage is being generated as it goes up. Now we're going to say this is 169 volts right here. All right? Now, this is called a sine wave because if you take the sine of any point along that rotation, because this is 0 degrees, right? This is 90 degrees. This is 0, effectively 0 again, right? It's 180. Down here is 270, which is the same thing as 90, right? And up here we're back to 0 or 360, right? So we've gone from 0 to peak back to 0. That's what AC does. It falls to 0 how many times a second? Once, twice. Falls to 0 twice a cycle. Not a second, a cycle. And here in the United States, we generate power at 60 cycles a second. So how often does AC fall into 0 if it's twice every cycle and there's 60 cycles a second? It's falling to 0 120 times a second. And it creates a noise that you'll begin to recognize. You'll be able to hear 120 cycles a second. Because when you hear a magnetic coil chattering, it's chattering at 120 times a second. It's jumping back and forth instead of being held in. We'll talk about that later. Okay, so this is called a sine wave because if you take the sine of any point along this wave, you find the proportion of the percentage of the peak. Now we've said that this peak is 169 volts. Everybody agree with that? Okay, odd number, right? Really and truly, that's what you're getting when you go over here to this receptacle over here. You're getting 169 volts peak. Okay? It might be 168.7 or a little below or a little above. It's around 169 volts. Now let's take 0 degrees. What's the sine of 0 degrees? 0, right? So, not too surprisingly, we get that. What is the sine of 90 degrees? It's 1.0. The sine, so 100%. Shocking, I tell you. Now, let's go over here to 45 degrees. What is the sine of 45 degrees? Pull out your calculators. Okay, so the sine of 45 degrees is 0.707. Now this is going to become a very important number to you. Okay? This is a very important number because this area under this sign right here is called the RMS value of this wave right here. And actually, this is not a whole wave, is it? This is a half a wave. And half a wave has a name. That's an alternation. Write that down, alternation. Half of a sine wave is one alternation. Okay? And this true RMS power here, what's 0.707 times 169? 0.707 times 169. 119.9 or somewhere around there. Let's call it 120 volts. Remember I told you that if you go to these receptacles around the room and you had a peak reading meter, that it would read about 169 volts? Yes, ma'am. What? It's the true RMS area. The true RMS area is what that shaded area is. The red shaded area is the RMS area. So the effective, now we call it the effective power of an AC wave. And what that means is if we were heating a resistive part with DC power, that we would need 120 volts of DC power through a resistor to have the same effect as this AC wave right here. So it's kind of a way of looking at what the AC wave is doing and what it can do, because it has this high peak and you have to look at it as an average. Okay? Now the same thing happens on the lower half. At 45 degrees, we're going to have this area here again, and that's going to be your true RMS power. Now, again, RMS is a part of the peak, right? And sometimes, not often, but sometimes we need to know the peak, we need to know the RMS, or we need to know something different. So let's look at this for a moment. Okay. Now, I want you to look down here and see this formula. RMS is equal to peak times 0.707. RMS is 0.707. In other words, at 45 degrees, we're going to get RMS. And that's what we're going to consider that whole alternation as 120 volts of RMS power. Root mean square. It's an average. It's an average. Okay? Now, if you want to find the peak, I want you to forget this formula down here. Just remember RMS equal to peak times 707. If you want to find the peak, what would you do to get the peak of this RMS equal to peak times 0.707? What would you do to that to get peak all by itself? You would divide by 0.707, right? So don't try and remember both these formulas. Just remember one. RMS is 707 times peak, right? So if we get peak by itself, we just divide both sides by 0.707. So we have RMS divided by 0.707 gives you the peak. Same idea as multiplying the RMS times 1.414. Because if you divide, it's a difference of base. All you need to know is remember the top one. RMS is equal to peak times 0.707. Okay? And I want to warn you that there will be a quiz on this material where you'll have to find the peak from one voltage and the RMS from another. And so you're going to have to do this a couple times. So you want to remember this formula. RMS is equal to peak times 0.707. And if you forget, remember that 45 degrees is the RMS point. Okay, so the sine of 45 is 0.707. And it's actually got a big long number, not just 0.707. Okay. Now, when we create AC power, it causes another problem in that the voltage and the current don't occur at the same time. Darn it. Okay. The voltage, the pressure, remember we talked about, well, maybe we didn't do this in this class, but in the first semester, you should have talked about when you create DC power, it's like that French toilet where the tank of water is the voltage potential difference, right? It's the ability to do work. And when you open the valve and let the water flow, you've got a current, right? So you've got that pressure before the current happened, right? Same thing with AC. You got pressure. Now it depends on what kind of circuit it is. Now this is kind of early to tell you this, but I'm going to tell you something new that is not in our chapter. There are two things. We're talking about inductance in this chapter, right? But I want to tell you now and get it out of the way that later we're going to talk about capacitance, and they're exactly 180 degrees out of phase with each other. So capacitance will cancel out inductance. And what happens in an inductive circuit is that one thing happens first, and in a capacitive circuit, the other thing happens first. And the way to remember which is which is Eli the Iceman. Eli the Iceman. Write that down. Eli the Iceman. I-C-E. Capitalized I-C-E. The Iceman. Eli the Iceman. Okay? And we're just talking about inductive circuits right now. But later we're going to talk about capacitive circuits. And they're in phase, 180 degrees out of phase with each other. They happen the exact opposite way. Okay? So let's talk about Eli. What does E stand for? Voltage. Electromotive force is voltage. What does I stand for? The intensity of the current flow, right? What do you think? Just take a wild guess. In this formula, it either leads or lags. Which do you think that is? So voltage leads current in an inductive circuit. Okay, that's true. Now, we know that capacitive circuits are 180 degrees out of phase. By the way, the symbol L, you've learned in this chapter, stands for what? Inductance, right? So this is really a good abbreviation. Eli, in an inductive circuit, voltage leads current. In a capacitive circuit, C for capacitance, right? What's first? Current leads voltage. Okay? So if you want to know which is leading, there's your memory trick. Because L is for inductance and C is for capacitance. And it's which one's happening first? Voltage happens first. And then in the capacitive circuit, current leads voltage. Okay. So that's just something we need to know later, but now is better, okay? Because we're talking about inductance. Okay. Skin effect. Electrons would like to go around the outside of things instead of going through the middle of a piece of wire. They just prefer to go on the outside. I can't tell you why. Physicists aren't sure why, but it's true. Okay, power generated in the world is alternating current. Why is it mostly alternating current generated in the world? Because you can transform it. Do you realize we use power here in Los Angeles that is generated in Arizona? Now, the higher the current, the more the voltage drop. From first semester, you should remember the 2 kilo over circular mill gives you voltage drop. Remember that? You can't change the size of the wire. If you're going to go from Arizona to here, you can't have 4-aught wire, can you? You can't afford to do that from Arizona to here. So you're going to have, let's say, number 2 wires the whole way. So you're setting the size of the wire in stone. Circular mill is going to be set. You can't do anything about that, right? You can, but nobody's going to pay for that. Nobody wants to pay for that. But what about, what's the other parts of the formula? 2 or square root of 3 for 3-phase circuits, right? K, can you change the copper constant? You cannot change that. I, current. Wait a minute, we can change current. How can we change current? We have 10,000 watts of power we want to transfer, or 10,000 volt amps we want to transfer one place to another. We can kick the voltage way up and the current will go way down, right? Okay, that's how we transmit power from Arizona to here. Okay? What do you think the voltage, transmission voltage is from there to here? In the millions of volts. Okay? In the millions of volts, because they want to get the power down. They want to have be able to transmit as much power as possible with as little voltage drop. The higher the current, and also the L in our formula, length, from Arizona to here, we cannot change this from Arizona to here, can we? The only thing we can change then is the current. And the only way we can change that is take that same amount of power and use a higher voltage. And the current is a proportion of that, because remember our formula about power, right? Okay. All right. Alternating current can be transformed and direct current cannot. Edison versus Tesla. Alternating current reverses its direction of flow at a periodic interval. Well, what they mean by that is if in Europe they generate power at 50 cycles a second, here we do it at 60 cycles a second. That's all they mean by that. And the frequency, the 50 cycles and 60 cycles, affects the inductance or the capacitance. Frequency, because what is our formula for inductance? Oh, that's the next chapter, right? Is that a grade? Review, we don't need to do that. Let's get into the next chapter. Instantaneous voltage at any point in a sine wave is equal to the peak or the maximum voltage times the sine of the angle of rotation. You guys are on that now, right? Okay, cool. And current and voltage in a pure resistive circuit are in phase with each other. In a pure resistive circuit. And nowhere else. If there's inductance, any kind of a winding, or there's capacitance, which is unavoidable, you're going to have something other than an in-phase power situation. Where should we go now? I like that. Okay, we're going to talk about inductance now. And we started to talk about it a second ago. Inductance in AC circuits. We're going to discuss the properties of inductance in AC circuits. What a surprise. Inductive reactance, compute values of inductive reactance and inductance. Doesn't that sound like they're talking about the same thing? Inductive reactance and reactance? I mean, inductive reactance and inductance. Sounds like they're talking about the same thing, right? But it's 2 different terms, okay? Discuss the relationship of voltage and current in a pure inductive circuit. Now, I want to tell you that last slide was talking about a pure resistive circuit, right? And I said pretty much there's no such thing as an absolutely resistive circuit, right? The wire itself might have some capacitance, or if it's wound in any kind of a winding, even one winding, it's going to have a little tiny bit of inductance, right? Well, the same is true of a pure inductive circuit. Just doesn't happen. Yes, you can wind a wire and it has inductive reactance. But you know what? It's got resistance too, right? So there's no such thing as a purely inductive circuit. There's no such thing as a purely capacitive circuit. There's no such thing as a purely. Remember I told you that when we do things in the AC, we're going to do in the lab, we're going to do things and we're going to have a calculated exact number we think it's going to come out to be, right? And then it's not going to come out to that. Every time it doesn't come out to that because it's AC, all right? Just take that right now. It's going to be different. It's not what you expect because there's no such thing as pure AC. There's no such thing as, not pure inductive, pure capacitive, or pure resistive. There's just no such thing. It's a theoretical idea. Okay. We want to be able to compute values for inductors connected in series or parallel. Now that's an important idea. Now what's an inductor? An inductor is just a winding. We take a piece of wire and we wrap it around our finger, right? Now, what did Tesla call his motors that he invented? AC motors. He called them rotating transformers. Why did he call them that? What's a transformer? Where you take two windings and you wind the input winding and the output winding around the same iron bar to create better inductive coupling, right? Why would he call them rotating transformers? Because the rotating windings were interacting with the outer windings, and so they were inductively coupled. And there was iron in this thing to make it work better, right? Okay? So the motor, so what he's saying is his motor had round rotor, a wound rotor. You guys now know what that means. It's got a winding in the rotor, okay? And that winding reacted with the stator winding, right? And that's why he called them rotating transformers. Okay, so we want to be able to add inductors, which are windings, and in series and parallel. And if you remember your series and parallel stuff from first semester, and you should, then that won't be a problem adding this stuff up because you treat them just about the same way. Okay? The nice thing about inductors is you treat them the same as resistors. When you add them in series, you treat them the same as series resistors. When you add them in parallel, you treat them the same as parallel resistors. So this is going to be easy, right? Just a review of first semester sort of. Okay. So here we see a wire with current going through it, and it's creating this magnetic field around it. And it builds up. You know, our wave goes up to 100% and then goes back down to 0. So the magnetic field builds up. And what happens when it starts going the other way? It collapses and starts going the opposite polarity. And it has another magnetic field. And that's inductive reactance. That's inductive reactance. That magnetic field that you're building, collapsing, building, collapsing, building, collapsing. That's inductive reactance. Okay? So there's your winding. We have, what is this a symbol for? An alternator, something that's making AC power, right? And you may have heard people say, I'm going to go to Home Depot and I'm going to buy a generator. But are they buying a generator? It's making AC power, isn't it? They're not buying a generator. They're buying an alternator. Misnomer. It's a misnaming of that device. That's a whole different opera. We won't get into that at the moment. Okay, so let's look at this. As the current goes up, remember our our voltage is going up from 0 to 169 volts. And as that happens, we're building up a magnetic field. Builds up, builds up, builds up. Then it drops back to 0, collapses. Now it's going to go opposite polarity and go from 0 to 169 opposite polarity. So it's going to build up a different polarity magnetic field, right? And so then it starts dropping back to 0 and collapses back to 0. All right. Now, one of the rules you'll read is that when you induce a current into a winding, that the induced current has the opposite polarity as the current that induces it, right? Isn't that a rule? You read about that rule? Somebody say yes. Okay. Really? Did you? Do you remember it? Probably not. That's okay. So here we have an applied voltage. We've got an applied voltage going through this winding, right? And it's going to create a counter EMF, a counter voltage, a reverse voltage. It's going to fight it. You know that thing about the law of physics, about something that's at rest, wants to stay at rest, something that stays at movement, doesn't want to change its speed and direction. If you've got a ball going down the road at 55 miles an hour and it's a steel ball, it doesn't want to stop, does it? It wants to keep rolling. It doesn't want to go the opposite way. And that is kind of the same thing as this applied voltage. The applied voltage is opposite in polarity to the current that created it. So we've talked about in first semester that you have pure resistance, and I call it pure DC resistance, right? The wire has a resistance to the flow of AC or DC, right? And I call that pure DC resistance. But when you have a winding, it has inductance, which is a resistance to flow of AC through the winding. Okay, and because of that, you're going to have less current flow because of this counter EMF. And the total of pure resistance and pure inductive reactance is called impedance. The total resistance to AC flow is called impedance. Write that definition down. You're going to have to repeat it back to me someday. Impedance is the total of pure DC resistance and inductive reactance. That is impedance, the impedance of a circuit. Current limiting property of an inductor. No, that's not a very good way of looking at it. It's creating a counter EMF. Now, the symbol for the inductive reactance is X sub L. And it's measured, and I think this should be a different term. Inductive reactance, I don't think should be ohms. I think we need to create a new term for inductive reactance. And I don't know who to talk to that about, but, you know, I'm not in that field, so I probably will never get the option of changing the name. But I think it should be a different term because ohms is pure DC resistance. Everybody knows that. So X sub L should have a different name, in my opinion. But we don't. We call it ohms. So you have to watch out when you see the term ohms, because sometimes it means pure DC resistance, sometimes it means X sub L, sometimes it means impedance. And what is impedance again? The total resistance to AC flow. Now, how do we find inductive reactance for anything? A winding. We've got a winding. And I've said that it, like a lot of things, is that it's dependent on the frequency. How often are we creating and collapsing that magnetic field? That's the real thing that's going to change how much inductive reactance we have, right? Look at our formula here. Our formula is 2 pi FL. And I'm going to teach you a shortcut for that later. Okay? Inductive reactance, that's the total resistance to AC flow because of the winding only, not the DC resistance. Okay? 2 is a constant. Okay? Pi is a constant, 3.1416, on and on. Frequency, it's always 60 cycles a second in the United States, right? Now, L, inductance in henries of the coil. Now, what does that mean? Let me tell you what that means. Look at this. 2 is a number. Pi is a number. In the United States, F is always the same. Yes? So let's change that, as long as we're here in the United States, to a number. What's the frequency? Okay, that's the frequency. What's pi? Okay, 2. So what you're saying to me right now is that 2 pi F is one single number. 376 point something. Multiply it out. Use the whole pi. Pull out your calculator. Hit clear twice. Now hit pi times 2 times 60. What number do we get? If you've got your calculator set, if you gave me that answer, that means you've got your calculator set to round a little bit. What did you get? 376.99. Now that's an exact number. But it's so close to 377 that we're going to call that 377. So we can, for as long as we're working in the United States or any place where they have the American electrical equipment, we can say that X sub L is 377 times the inductance in henries. Now that's something that if you buy an inductor, you can find it. Can you measure inductance? Is that on your meter? Has anybody got their Fluke 117? Not with you, but that's okay. You could measure this. This is something you can measure. Okay? It's difficult. Most people don't know how to do it. That's okay. And we can also back into it, right? If we know the total impedance, we can back into the X sub L, go the other way and find out everything else, right? Okay. Okay, here we have an inductor. This right here, inductor. This is tightly wound. I want you to notice, though, that they're wound the same way. You see how this one's in the back over here? This one's in the back. This one's in the back. What if they were wound in opposite directions? Would that affect anything? You bet it would. Because the winding is going to affect the polarity of the magnetic field, is it not? Because this thing is going to create a magnetic field. What did Fleming say about this? Does anybody remember first semester's? Was there some left-hand rule in first semester? Fleming's left-hand rule? And there was a thumb, a finger, and your coiled fingers. And your coiled fingers represented the direction of the windings. They're going around this way, right? Well, what did your finger represent? Magnetic north, maybe. What did the thumb indicate? Current flow direction, right? If this is the current flow direction, if the windings are this direction, then we're going to have a magnetic pole that is pointed this way. And if the windings go the other way, then we have to look at it the other way around, right? So Fleming, and the funny part is Fleming figured this stuff out before there were batteries to speak of, before there were wires to speak of, before anything except some really smart people. Okay? So, okay, things that affect inductance or the induced voltage, the number of turns in a wire, the strength of the magnetic field, the speed of the cutting action. Remember when we're generating, the faster you spin it, it's going to affect the voltage. You knew that. If you spin a generator faster, it's going to create more voltage. Kind of simple, right? Okay. And then let's look at inductance AC. Here we're going to find, if we know that this is 0.8 henries, we can find out the total X sub L of this coil, right? Now, we're not talking about yet is this combination thing going on here. Does this coil have a resistance, a pure DC resistance? Of course it does. And just like all AC circuits, nothing's as simple as this right here. Okay, we'll get to that in a minute. So if we want to add up inductors, we say the total inductance is L1 plus L2 plus L3. Isn't that how we add up resistors in series? So we treat them the same way. That's the trick to the memory. Just treat them inductors. You treat them like they were resistors. The same rules apply. So in series, it's nice and simple. In parallel, it's just slightly different. You've got that 1 over RT thing going on, right? So let's look at that. Let's look at parallel. Well, look at that. 1 over LT. Wait a minute. If this were resistors, if we're adding 3 resistors in parallel, we would be saying 1 over the resistance total is equal to 1 over the resistance of 1 plus 1 over resistance of resistor 2 plus 1 over the resistance of resistor 3, right? But it's the same thing, except we're saying the inductance instead of the resistance. So we treat them the same as resistors. That's a good thing. Makes it nice and simple. Now, we talked about Eli, right? And here's your trick to remember Eli. The applied voltage, oh, look at that. The current is somehow, what is Eli? E, the voltage before? Oh. Okay. So, what happens in a circuit that has an inductor is you create 3 kinds of power. In any circuit, you have 3 kinds of power when you have an inductor. Now you have apparent power. What is apparent power? We talked about that in first semester. Apparent power is whatever voltage and current is going in, and it's called volt amps, right? Nice and simple. It's volts times amps, right? We have 120 volts going in at 10 amps. We have 1200 VAs. Nice and simple. What is Edison charging you for? Volt amps. What do they say they're charging you for? Watts. A watt. Watts is true power, the actual work getting done, right? Well, you've got an inductive circuit. It's not perfect, is it? You're not getting everything out you put in. If you're putting in 1,200 VAs and you've got an inductive circuit, are you going to get, which every motor is an inductive circuit, right? So if you've got a pool pump in your backyard, are you going to get 1,200 watts of work out of that pump? Heck no. You'd be lucky if you get 70% or 80%, right? Why is that? Because there's an energy being used to do what? Create that magnetic field? I don't want to pay to create a magnetic field. I don't like that. We'll figure out how to change that later, okay? Not right now, but we're going to figure out how to do that. Now, that's like heating wire, inductance, resistance in a long circuit. We can reduce that too, right? There are a couple of ways of doing that. Okay? So to find, let me finish explaining. So you have apparent power, that's what you're putting in. You've got some true power of the work really getting done. Let's say it's 70%. Okay? So what's 70% of 1,200? What doesn't matter? 800 something? 840? Something like that. Okay? So you could be getting 840 watts of actual work coming out of that motor, right? About. Now, there's going to be some other power that's happening besides just that power that's not making true cranking force. There's a thing called VARs, volt amps reactance. So it's like apparent power, but it's the reactive power. And the formula for that is the inductive voltage times the inductive current. Well, that's not very helpful, is it? But what it is it's the power that's created through building and collapsing that magnetic field. So it's energy that's being, I won't say wasted, but it's being used to build and collapse the magnetic field. Okay? I want to tell you one other thing before I want to talk about AC or motors just for a second. When we start up a big motor, we talk in motor control about how there's a big current inrush when you first plug in the motor, right? You know why that is? Because the magnetic field in those windings has not built up yet. So there's no counter EMF. So the only thing restricting the flow of current through that winding is the pure DC resistance, which is much higher than the total impedance. Much lower than the total impedance. Because once you build that magnetic field up, it's going to slow the current flow down. Because you're going to be spending some energy creating that magnetic field and collapsing it, right? And so when you first start a motor, it's going to flow its pure DC resistance only, which is going to be anywhere from 4 to 8 times what your normal full load current would be. And that's why we have to change the size of the things when we look at motors. Okay? So once that field builds up, the current flow goes down because of the inductance. And now we're creating VAR, volt amps reactive. So reactive volt amps, they're power that's being used. Now, do you think that if you add up the true power and the volt amps reactive, that'll add up to the power that you put into the circuit? Absolutely not. AC doesn't work that way. Things add up? Nope, we're not doing that. How do we do that? With a triangle. We'll talk about that in a minute. Okay, now let's get rid of, just add a slide. New slide. Thank you. There we go. All right. Okay, now, in first semester, in DC theory and the math class, basic math for electricity and electronics, you learn to use PEIR, right? But now we're talking about AC, so we're going to take out R because you now know that most AC circuits are not just pure DC resistance. They have impedance, which we call Z for impedance. Okay? And so let's look at a motor. Let's look at a motor. And we're going to say that this is a 120 volt single phase motor. So our total voltage is 120 volts, right? Do we see that? Okay. Now, let's say that if we take this motor and we read the pure DC resistance of the windings, and let's say that we get 20 ohms of pure resistance. Now, we're always going to put these triangles, where I'm starting a little early on this material, but that's okay. We're going to work on this a whole lot. We're going to work on this all semester, okay? So it's real important. So if we have 20 ohms of pure DC resistance, and let's say that we know, for some reason, we measured the inductive reactance of the winding. And let's say that we have, 15 ohms of X sub L. From that information, remember our 2 pi FL? We could find how many henries this coil has, couldn't we? We'd have to back into it, right? We'd have to say that 15 is equal to 377 times L. So, in other words, 15 divided by 377 gives us the number of henries, yes? All right, so we're off to a jump. Now, from triangles, you recognize that you have a side opposite, which is X sub L, and a side adjacent, which is side R, right? So if you have your formulas, oh hell, another hour of agony from first semester, we can see that we have a tangent, don't we? We have a tangent. Uh-oh. Did I just lose everything I wrote? Oh, I hate when that happens. Okay. Start over again. P, E, I, C. We hit. All right. So now we have our drawing back. Sorry for the delay. Now, we've measured 20 ohms in the circuit, right? We also took a special meter. We read the inductive reactance. It says it's got 15 ohms of inductive reactance. So that tells us that we have a tangent function. So pull out your TI hand again, TI 30x2s, hit clear twice, and now I want you to put in second function tangent. 15 divided by 20 is equal to, and that's going to tell us the angle, is it not? Okay. So what is my angle? We've got a big long number. We want to hang on to that number, right? Because we want to work with an exact number with a lot of numbers behind the decimal. So 36.8 and a whole bunch of other numbers behind it. Let's not leave that. Let's leave that in our calculator because we want to find something else now. Because we're looking for the hypotenuse, right? So as we look at since we have sine, cosine, tangent of any, we have the angle, so we can find the sine, the cosine, or the tangent. We can find the relationship between the opposite and the hypotenuse, the adjacent and the hypotenuse, or we already have this one, right? And that's how, from the tangent, we found the angle. So now, oh no. So now we can say, let's use the cosine and find the hypotenuse. Okay, so we've got an angle in our calculator, right? Yes. So hit cosine, just hit cosine first. Now hit second function, answer, enter, and that just took the cosine of the angle we just found, right? 0.8 even. I love that. So our cosine of theta is equal to 0.8000, right? Anybody agree with that? Just take my word on this. It's true. I picked those numbers for a reason. Okay? So our impedance, we're looking for the hypotenuse, right? We want to know what this is, right? So if the cosine is 0.8, that's equal to what? A, don't we know A? Side adjacent is 20, right? 20 divided by the hypotenuse, which is what we're looking for. Everybody agree with that? We call that Z in this particular case because it's the impedance. Okay? Now, I told you many times before that in first semester, you can take this number and this number or symbol and reverse them, right? And it's still a valid formula. So we're going to do that now. So we have H is equal to 20 divided by 0.8. So now, what do we have on our calculators right now this second? 0.8, right? So let's put in 20, just punch in 20, hit divide by, second function answer, which plugs in the last number we found, which was 0.8. We're going to divide by 0.8, and now we have, say again, 25. So H is equal to 25. So our impedance is 25 ohms. Everybody see that? Okay, where are we going to take that information? We're going to plug that into our PEIZ, and that will now give us an apparent current, right? The current that's going to flow in this thing. And if we multiply that current times 120, we'll find the total power. Everybody agree with that? So what's in our calculator right now? 25, right? Now to find I, we have to divide E by Z, right? PIE EIR. E divided by R gives us I. Everybody agree with that? So 120 divided by what's in our calculator right now. So let's just put in 120 divided by second function answer, and we find 4.8. Now 4.8 is still in our calculator. Is that correct? Yes. Times 120, and we get by what? No. VAs. That's apparent power. That's what we're putting into this circuit. Are we getting that much work out of it? No. But I'm going to show you how we find that. Now we're going to take this information right over here. That's the apparent power. Didn't I just say that? Let's get rid of this. And this right here. I'm going to say that our apparent power is our hypotenuse, because it is every time. 576 VAs. Now, we have some other information we already found out, right? That our cosine, oh no, I just lost all my drawings. We still know that our cosine what was that, 36.8? Okay. And our cosine of theta is 0.8. Everybody agree with that, right? Now, this is our new triangle. This is our power triangle. We're pouring 576 VAs of power into this circuit. And we'd like to know how much work we're going to do, right? All right. The cosine is equal to what? Oh, hell, another power. Okay. Don't we have hypotenuse in this case? And we have the cosine? Wait a minute, that's two solid numbers. So the cosine is 0.8, right? And it's A, which is kind of what we'd like to know, which is our side adjacent, which is our true power. And so A over H, we know what H is, don't we? Wait a minute. I can get A all by itself just by multiplying both sides by 576. Everybody agree with that? So 80% of 576 is what? How much? That's how many watts are being cranked out. Just a minute. We're going to practice lots of times. You don't have to. Okay. Because we found we had the hypotenuse. We multiplied the voltage times the current. We've got our apparent power. We know that this angle, this phase angle, is the same angle as our resistance triangle, right? So we can use the same angle. And the cosine is for the same angle, the same cosine. So the cosine of this angle is 0.8. This is our apparent power, right? We multiply the cosine times the apparent power, we get the side adjacent of the true power. Okay, now I know this is a lot. Don't worry about trying to learn all of this at one time. Don't panic. We're going to do this a bunch of times in the future. This is just a preview. All right, this is just a preview. You don't need to do it right now. It's a second. But now, what if we wanted to find out how much, I can't talk, reactive power this thing's going to make? Let's look at the sine. What is the sine? Oh, hell, right? The opposite over the hypotenuse. We know the hypotenuse, right? We know the angle, but let's find the angle again. Hit clear twice. Let's go back and find the angle again. We know that it was second function tangent 15 divided by 20, right? That's to get our exact angle. Everybody agree with that? Everybody remember that far back? Go ahead and do that now. Second function tangent 15 divided by 20 is equal to, you should get 36.8 and a whole bunch long number, right? Now hit sine, second function answer, and that'll take the sine of that angle. What do you get? 0.6. I knew that was going to happen. I can't tell you how, but our sine is 0.6. Okay? That's our sine. That's the sine of the angle, right? And that's equal to the opposite, which we would kind of like to know. The side opposite. This is our angle. And so the side opposite is this one over here. We want to know the side opposite. And the opposite over the hypotenuse, which is 576. Look at that. If we multiply both sides by 576 again, multiply the hypotenuse times the sine, it'll give us the side opposite, which is 345. Now I want you to notice this. This is 345.6 bars. Both amps reactive. Both amps reactive. Okay? Now I want you to notice that 345.6 plus 460.8 is what? Way more than 576. Once again, AC doesn't add up. And that was the point of this whole discussion. Remember, it's not going to add up. Don't get in a panic about it. Okay? Now we get rid of all this. Okay. And I believe that we're going to end today on that note. Is everybody okay? Any questions? Any questions? Yes, sir.
I know other teachers like to teach the Pythagorean theorem.
Don't. Stop. Stop. I'm glad you brought that up. Now, what are we doing here when we did those two different triangles? I have a name for it. I've created a name for that. Nobody else uses my name for it, but I don't care. I call it simultaneous triangles because they both have the same angle. It's called the phase angle. And the phase angle for any AC circuit is the same phase angle for any part of that circuit, right? The phase angle is the phase angle is the phase angle. So if we solve the resistance triangle and we use angles and we find the angle, then we can find the other triangle totals, right? But if you do it by Pythagorean theorem, that's quick and easy. You learned it in the 4th or 5th grade. It's nice and easy. But what do you do when you go to the next triangle? You got an angle. Well, you don't, with Pythagorean theorem, you don't even get the angle. So you got a side. Now what are you going to do? Now you're screwed. Now you can't move forward anymore. So we're always going to use triangle angle manipulations instead of Pythagorean theorem. From now on in AC, we're always going to do that from now on. Do not do it with Pythagorean theorem unless you don't need any other information except what is this side over here. In other words, just don't do it. Just don't do it. All right? Pythagorean theorem, erase it from your memory. Pythagoras, nice guy. He found out how much property he had if this side was this side was this, and we're dividing this property in half between me and my neighbor. That's what he found out. his formula was about an argument over property. Okay? We're way past that. Okay? Yes, ma'am.
So reactive power is all the part.
The power that is used to create and collapse that magnetic field. That's what it is, to create that magnetic field. Okay? That's what reactive power is. Does that sound like a waste of energy? Yes, it is. It is a waste of energy. And we're going to find out later in this class how to get rid of it. Get out of here! We need reactive power? Absolutely not. A perfectly tuned circuit has a 0-degree angle, or very close to it. And what is the power factor for something who's 0 degrees? 100%, right? Cosine of that angle, cosine, I shouldn't be telling you this early, but the cosine of the angle is the power factor. How much power is going to be converted from input power to watt, cranking force, in the case of a motor. Okay, did I hit stop? Damn it. It's all right. That's okay. You're going to, wait a minute. Don't worry about it. You're going to hear all that again and again and again. What we just talked about is what we're going to do all semester long, mostly. Okay? Except you're going to add up parallel resistance. Because if you look at a motor, how many windings does the motor have? Does it have just one winding? No. Some do. They have one input winding, one armature winding and a field winding. And you can look at that as all one winding, sort of. Maybe. Yeah, some do. But how about a three-phase motor? Can you look at a three-phase motor as one winding? Don't hold your breath. Oh, that's a combination circuit. Oh, shoot. It's going to get hard. Oh, no. It's easy. Don't worry about it. Don't worry about it. When you get to the end of the semester, you're going to be looking at stuff we talked about at the beginning or in the middle, and you're going to go, I'm sure glad we didn't talk about that. That looks hard. Time to get up. All right. Take a break. See you in the lab at 11 o'clock. Thank you. Is everybody having fun? Yay! This podcast will be on in about an hour. Okay. Good one? Good one? All right. We have fun now? All right. Don't lie to me. It's okay. Are we equally unhappy? Yes. Yay! All right. Thank you. Wait a minute. If you did not turn any homework in, I need you to do something. I need you to take a piece of paper out, write your name in the upper left-hand corner, write no homework. Yes, you too, Soraya. I know. It's okay. This is a record-keeping thing for me. If you didn't turn any homework, that's how I keep. I don't want to count your noses. I got too much stuff to do. Okay. If you didn't do any homework, just one piece of paper will do. Put your name block. Okay, except for the chapter, and write in the middle 0, no homework, and put it in that pile right over there, where the homework should have gone. So that way I know you were here, but you didn't turn anything in, so you're actually here, but. Okay? Are we clear on that? Anybody not clear on that? Is everybody confused? No? Yes? Good. Don't worry about it. We're going to clear that fog. Huh? Oh.
So you got that last part.
Oh, good.
Yeah, you can just go back.